Welcome back. Very prolific hydrocarbon provinces are hosted in extensional systems such as continental rifts like the North Sea and passive margins like in West Africa or South America. In the slide, you see a generalized section across a rifted continental margin. You can recognize easily the normal faults and the sedimentary succession deposited prior to, during and following rifting. We've called these pre-rift, sin-rift and post-rift respectively. In the post-rift, you can see a carbonate succession overlain by siliciclastic with a combination of silts and sand. The source rocks are generally represented by lacustrine or shallow marine deposited, sedimented in the small and isolated grabens which develop during the initial stages of rifting. These rocks subside during and following rifting and start producing hydrocarbons when they reach the oil and/or gas windows. As we have seen, it is of crucial importance to determine if, when petroleum generation started, the traps were already in place or not. The hydrocarbons will start migrating upward along the tilted beds overlying listric faults and/or along faults. Rift systems, such as the one shown, have various potential reservoirs. A first type is associated with the tilted blocks with the seal formed by the unconformable fine-grained rocks deposited during the initial stages of the post-rift. Traps are often also found in carbonate succession deposited during the early post-rift. Hydrocarbons migrating mainly along the faults manage to enter the post-rift and can accumulate in porous facies associated, for instance, with carbonate rift buildups. Hydrocarbons can also further migrate upward, entering sand bodies in the siliciclastic part of the succession, often associated with turbidite and pelagic sedimentation. Various extensional systems are characterized by the presence of thick succession of evaporites, typically deposited in the early post-rift stages. During post-rift deepening, the evaporites become mobile, start forming huge columnar bodies kilometers high. Salt is a perfect seal and is a key component of some of the largest hydrocarbon fields, such as the recently discovered in the offshore of the Brazilian margin. These subsalt fields are sourced by sin-rift succession and produce more than 1 million barrels a day. Continental rifts and rifted continental margins have been studied for a long time, but they remain extremely important exploration targets. Boreholes are being drilled in ever deeper water conditions, even targeting reservoirs underneath the salt in domains which are very difficult to image from a seismic point of view. The challenge continues. Welcome. Hydrocarbons are also very common in regions that have experienced substantial shortening, such as fold and thrust belts. Large productive fields of this type are found, for instance, all along the frontal part of the Rocky Mountains in Canada and in the US, and in front of the Andes in Bolivia and Colombia. Fold and thrust belts develop in the external domains of regional collisions between two continental plates. Shortening causes thrusting and the formation of a pile of thrust sheets stacked upon each other. In the vertical cross-section, you can see the most important components of the system. In the deep part of the section, you see the rifted margin succession, which includes grabens formed during rifting and the post-rift sediments. The upper part of the section is characterized by two main units. The first one, which you can see on the right, are the thrust sheets resulting from regional convergence. These form thrust-related folds and pile up, creating an extra load on the lithosphere. As a consequence of loading, a 4D basin develops in the front of the advanced origin, mostly hosting interregional sediments produced in the mountain belt. At the transition between the two domains, you can see that new thrusts are activated, involving the sediments deposited in the foredeep. As convergence continues, parts of the foredeep succession are thrusted and incorporated into the origin itself. Now, this is what a typical hydrocarbon play in fold and thrust belt looks like. The source rocks are typical marine sediments being deposited during the post-rift stage, preceding shortening, or in the initial shortening stages. They generate hydrocarbons, which will migrate upward, often along the thrust faults, and will accumulate in traps. The most common type of trap is related to the faults developed during shortening. Alternatively, hydrocarbons might accumulate in sand bodies in the terrestrial succession in the 4D basin itself. A key challenge in fold and thrust belts is the relative timing of a hydrocarbon generation and trap formation. If hydrocarbons are generated too early, when the faults are not present, then they might simply reach the surface with no accumulation. Reservoirs associated with anticlines in the external zones of fold and thrust belts are often quite superficial and have been known for the first discoveries made in the history of the hydrocarbons. At present, most of these targets have been already identified, and exploration is directed towards deeper targets. This is very challenging and high-risk exploration. Welcome to the last module of the GeoMOOC. By now, you know everything on how rocks are formed, how the Earth works, and also something about hydrocarbons. The time has now come to tackle what is possibly the most important commodity of all, water. Everybody needs water, and societies need it too. The water we use comes in large portions from river, followed by groundwater, and in smaller amounts from marine water. We use water for a variety of purposes, mainly industry and irrigation, and only a small part for public use like drinking and taking showers. Water resources are in many countries under great pressure because of a combination of factors. A profound knowledge of the hydrologic system is a prerequisite for the responsible use of water. In the cartoon, already known to you, you see the water cycle. Waters evaporate from the sea, rise, and depending on circumstances, fall back as precipitations. We have looked in previous models to the water flowing on the surface of the Earth. It is now time to start looking to what happens to the water infiltrating the outer part of the Earth. In the hydrogeology cycle, the first component is recharge areas. That is, the places where water enters into the ground. The most important of all areas of recharge are those with large precipitations. We have seen in previous models that mountains, especially on their windward side, are great recharge areas. In specific conditions, also water bodies such rivers and lakes can also form recharge areas. We will see at a later stage how this is possible. The water infiltrating the underground in the recharge areas will enter high permeability layers, partly or fully saturating them with water. These layers are called aquifers, and they contrast with low permeability layers called aquithards. Water in the underground can follow two paths, and being stored in unconfined or confined aquifers. If the uppermost part of the underground is composed of permeable layers, then the waters will accumulate in these rocks, forming an unconfined aquifer. An unconfined aquifer is therefore an open system. Being close to the surface, unconfined aquifers are the first one to be used by all communities and are increasingly under pressure. If in the recharge area permeable layers are found which dip steeper than the topography and therefore continue deep in the subsurface, the waters will flow along these layers, forming confined aquifers. Differently from what observed for unconfined aquifers, they are bounded by two low permeability formations and are fully saturated with water. Confined aquifers are deeper and more difficult to access, but have clearly some major advantages, like the fact that they are protected from negative effects from the surface and that they typically have clean waters. To keep water flowing, the hydrological system obviously needs also discharge areas, that is, domains where the water leaves the aquifer and goes back to the surface. Rivers and lakes are common discharge areas. Others are springs, like the ones you see in the figure. We mentioned that water systems are under pressure in a variety of situations. Here you see some examples. I don't think that we need much explanation to this. An interesting example is from rural communities in Niger, where I worked many years ago. Precipitation in the air are very low, below 200 millimeters per year, and erratic. Villagers generally take water from small ephemeral lakes and dig few meter deep wells where water quantity is variable and quality generally poor. In the area, like in many places in North Africa, there are confined aquifers, but they are a few hundreds of meters deep and can only be reached and produced with advanced technological material. Communities have then started digging wells several tens of meters deep, which reach partly confined aquifers hosted in small lenses of sand, water of better quality. The challenge is then to predict the extension and depth of these bodies so that they can be reached by traditional wells. In a very different setting, agriculture is surely one of the most important challenges to water resources, as agriculture needs a lot of water. An apparent example is provided by the High Plains Unconfined Aquifer, one of the largest aquifers on Earth. The result of very intensive agriculture activities and proportional use of water has resulted in a major depletion of the groundwater reserves. Clearly, we are not using water in a sustainable manner. In addition, agriculture in many places still uses large amounts of chemicals, which flow back into the unconfined aquifer, polluting the water. Careful management is absolutely needed in these conditions. Already from these first few slides, you see that hydrogeology has a lot to do with flow and fluxes. A quantitative knowledge of such fluxes is a necessity for geologists and hydrogeologists. And I want to give you here a very few basic ideas. Fluxes of water into, through, and out of the aquifer are combined into the hydrogeological balance, which is essentially conservation of mass applies to water. What comes in has to go out. This is the general equation of the hydrologic balance. If the various components, or at least their total contribution, remains constant, then the volume of the water in the system will not change, and the water table will not change its position. You can look in detail at the scripts for this more information. Let us now imagine that we drill a well and start pumping. The system will react and reach a new steady state, which calls for an increase of flow into the drill volume. If this is not sufficient, there will be a decrease in water volume and of the water table. Clearly, a non-sustainable situation, unfortunately one which occurs more often than one would like, is being generated. From the small flow exercise above, it is clear that the correct definition of the geometry and the physical properties of the aquifer is key to successful management of water resources. It is up to the geologist to use available data, interpolate between wells to create a viable hydrogeological model for the subsurface. This might be relatively easy for superficial, unconfined aquifers, but becomes more challenging for confined aquifers, which might be hundreds of meters deep, or even much more for geothermal fields, often located at depths of several hundreds of meters or even few kilometers. Great challenges ahead. In this clip, I will present some general features of water and of the porous medium across which it flows. Several aspects are similar to what we have already discussed for hydrocarbons, but there is also some important differences. This is what a water molecule looks like. You clearly see the oxygen and the hydrogen atoms. You also see that as a consequence of their asymmetric arrangement, the water molecule has a positive and a negative end. A very important property of water is its density, which is around 1 gram per cubic centimeter. At temperatures relevant for hydrogeology, these values don't change much. Things are different, however, at high temperatures, and for instance at 60 degrees, the density of water is 0.97 gram per centimeter cube, which is a big enough difference to cause vertical movements in the thermal system. Let me show you immediately an example of the importance of heating. When cold water descends towards deeper level, it will be heated and it will then start moving upward because of decrease in density. If the permeable layer is sealed by an impermeable one, then convection cells are generated. If faults are present, then the hot water can travel along the related fracture zones and possibly reach the surface, forming high-temperature springs. The density values we have mentioned are for pure water. When this is not the case, things are different. In a previous clip, we've discussed turbidites, currents which travel for hundreds of kilometers down the continental slope, driven by their density higher than the surrounding water. An effect of density contrast is also seen in coastal regions where fresh, low-density water from the continent overlies a tongue of denser saline water from the sea. As we will see at a later stage, preventing the continentward displacement of salty water is a major challenge in these coastal domains. Another important property of water is viscosity, which is a kind of internal fraction of the fluid resisting its flow. In a more precise manner, it can be defined as the parameter mu in the equation, which describes the force needed to keep the upper plate moving with respect to the lower one. Values are clearly much less than those of oil, and on the whole, clean water has no big problem in flowing, especially at the rates relevant for hydrogeology. Water flows through pores of a medium, which can be everything between loose sediment and a real rock. In these cases, surface tension and capillary forces are important. Because water molecules are attracted to each other, they form a superficial resistant layer aptly used, among others, by insects. In contact with the glass surface, water does not spread homogeneously and forms a bubble, this being also an effect of the surface tension. In average type of rocks, things are different, and water spreads easily, forming a thin film of fairly homogeneous thickness over all grains between 0.1 and 0.5 micromillimeters. This seems not much, but it means that grains will be water wet even if the rock is well above the water table. It means also that some of the smaller pores between the grains will be occluded by water, holding the grains together. Children or adults alike, building castles on the beach know very well how to exploit capillary effects to improve their building and achieve steep walls. The porosity in a sediment or rock exerts a fundamental control on the ability of a fluid flow to through it. We've seen in Module 5 that the main features control porosity and permeability. In granular rocks, porosity is the space between the grains and depends on the grain size and the degree of sorting. A very important source of porosity and permeability is also provided by fracture networks. These are particularly relevant for deep reservoirs targeted by geothermal projects. A last important issue I would like to mention at this stage concerns the interaction between the flowing fluid and the surrounding rock. At the mechanical level, infiltration of water in mechanical discontinuities can destabilize, for instance, mountain flanks, triggering landslides. Interesting are also the chemical interaction between the water and the surrounding rocks. Waters are typically carrying varied ions and cations, and the appropriate conditions can start precipitating minerals such as calcite. This is a very important phenomenon impacting, for instance, the permeability of faults. On the other side, waters can also dissolve the surrounding rock. This is especially the case for carbonates, resulting in spectacular karst structure and large underground caves. Having given a number of key definitions, we are now ready to look at how water flows. The motor driving flow is obviously energy, and not surprisingly, flow goes from places of high energy to those of low energy. The energy of a given water mass depends on compressibility, its vertical position above a reference level, and on the velocity with which it moves. These factors are quantified by the Bernoulli equation. The Bernoulli equation defines the amount of work needed to bring a given amount of water to its present state from a reference initial situation. Normalizing for the mass, we obtain H, which is the hydraulic head, usually referred simply to as head. This is the key word you need to remember. A further simplification can be obtained observing that the velocity of water flow in general is low, and therefore the last term of the equation can be neglected. This is the equation one can use to determine the hydraulic head of a water body. Let us look in some more detail at the meaning of a head, first considering only one well in a static situation where no flow takes place. When you dig a well, water will enter the borehole and will reach a level equal to that of the surrounding water table. We will call Z top the height of the water level with respect to a reference horizon, which is also indicated in the figure. Using the head equation and assuming that the pressure at the top of the water column is in the well can be neglected, you can see that the head is equal to the height of the water level with respect to the reference horizon. One can also determine the pressure inside the water column into the well. At each point, it will be equal to the depth of the point with respect to the water level times water density and gravity acceleration. Let us now look at the situation with two wells. Using the rules mentioned above, you can clearly see that well A has a head larger than that of well B. If possible, water would then tend to flow from A to B. The pressure at the bottom of the two wells depends on the height of the well itself. In the case shown in the figure, the pressure at the bottom of well A is larger than that of well B. Determining the head difference between water bodies and thereby predicting the direction of flow between them is crucially dependent on the establishment of a common reference level. In small regions, this is relatively easy. In larger areas, this is much more complicated. This is surely the case for the Netherlands, but it is a very important one, as more than 30% of the country is below sea level. Here, engineers have defined a reference level called NAP, and this is of crucial importance to predict if water will flow, for instance, towards or out of the polders. A very precise definition of the NAP is key to keep our feet dry. Now that we have the motor, we look at the flow. The two wells 1 and 2 shown in the picture have different heads, and water will flow from 1 to 2. Discharge across the layer is described by Darcy's law, which we already seen while discussing petroleum geology. The discharge is proportional to the head difference and to the hydraulic conductivity, which is a property of the porous medium. A useful parameter is the specific discharge, which is the discharge normalized by the surface across which the fluid flows. The specific discharge provides a description of the average velocity of the fluid, water in our case, across a unit surface. What one extracts from the equation, however, is only an average velocity. In reality, water will flow only through the pores of the rock and not through the entire section. A more correct description of the system needs to be done, which includes also the connected porosity of the rock. Real velocities will then be significantly higher. Darcy's law has some significant limitations which should not be forgotten. It is valid for non-turbulent flow and for systems which are characterized by one density, always constant. The key lithologic parameter in Darcy's equation is the hydraulic conductivity. Looking at the table shown on the slide, you see that conductivity values for different types of sediments and rock can vary by orders of magnitude. Correct predictions are challenging, but of great importance. Always remember that one value is generally not enough. Rocks at the scale of water reservoirs are highly heterogeneous, laterally and vertically. We have seen some of these issues while discussing petroleum geology. In the summary slide, you see unconfined and a confined aquifer. Aquifers and aquitard have very different permeabilities, and therefore the rates at which water will flow are also very different. The numbers show the typical time needed for waters to flow from the surface to a specific place. Huge differences. When tapping in confined aquifers, you might be drinking fairly old water indeed. More will follow.